So Akif is working on proper using in the hydrofracturing of coal seam gas reservoirs. So can I ask Akif to come to the stage?
Good afternoon, everyone. My topic is proppant usage in the hydraulic fracturing process during coal seam gas extraction. So today I'll be giving a brief introduction about my topic. What are the research gaps in the literature? Based on that, what are my research aims? What have I proposed for the next 2 to 2.5 years? What have I done so far and what I'm hoping to do in the future? So we know that more than 80% of the world energy demand is dependent on fossil fuels. But the problem with depending on fossil fuels is it's a depleting energy resource. And because of that, number of energy alternatives have been introduced. And one of the critical energy alternatives is natural gas. And in our focus, we will be speaking about coal seam gas. Now, coal seam gas exists in deep underground reservoirs. Now, these coal reservoirs are normally composed or comprised through the coalification process. Now, when you take one of the coal reservoirs and their composition, the main primary element is carbon. And then you will have small amounts of ash and moisture. And then our focus, which is the coal seam gas, it's around approximately 10 to 20%. If you take the gas composition here, the primary gas composition is methane. And if you take methane, this is a very valuable energy resource which can be used for energy production. And therefore, extracting this methane or coal seam gas is of primary importance. So in our research, actually, we are looking at how can we extract this gas in an efficient manner. So one of the ways of extracting is through the hydraulic fracturing technique. Now, hydraulic fracturing technique is where once you locate the reservoir, you drill until you find the reservoir depth, and then you go until as the design tells you how much length do you need to go, and then you inject high pressure fluids so that these fractures, micro fractures, are created in this reservoir. And when the pressure is depleted, the gas in these fractures are accumulated in this wellbore and separated at the surface. Now, if I take one of the fractures here, it will look something like this. But as we know, when you go deeper and deeper, the stresses increase. And when the stresses increase, it will act on this reservoir, and then it will act on this fracture. And past studies show because of this fracture begins to close or completely heal, reducing the productivity. So to combat this problem, what we do is we use proppants. So proppant-based hydraulic fracturing. Now in proppant-based hydraulic fracturing, basically what you do is you mix the proppants with the injection fluid, and it's expected that these proppants will go into these fractures and resist the fracture closure. Now these two are the primary ways of doing hydraulic fracturing in terms of this concept. Now if you take shale and siltstone reservoirs, their depths are normally more than 2 kilometers. So normally it is very common to see that they use proppant-based hydraulic fracturing. But what about coal seam reservoirs? There are coal seam reservoirs, the depth varies a lot. Now if you take some of the examples here which I listed down, the Westfield South Australia is close to the surface. But if you take the Cooper Basin here, it's more than 1 kilometer. But if you take the hydraulic fracturing depth, due to economical feasibility, normally it's less than 2 kilometers. So the question arises, do we actually need proppants to use to extract coal seam gas? And if we do, at which point, at what situations do we need proppants to use to extract coal seam gas? Now this needs to be investigated. Now if we assume that, okay, proppants are needed for coal seam gas extraction, there are 3 main proppant degrading mechanisms that we can expect during the hydraulic fracturing process. First one is proppant crushing. Now proppant crushing is once you reduce the pressure, the effective stress increases, and then when the effective stress increases, and if it exceeds more than the compressive strength of the proppant bag, the proppant crushes. This proppant crushing will reduce or will allow the fracture to close. But if you take coal seam reservoirs, as I said, it's less than 2 kilometers, and normally the effective stresses developed are between 10 to 20 megapascal. But if you take the main propping agents used here, are sand, resin-coated sand, and ceramic proppants, their compressive strength is much higher than these effective stresses developed. So this may not be the most plausible damage mechanism that we can expect. Now the second one is proppant diagenesis. It is basically the change in physical properties, the change in texture, the change in mineralogy. But for this also to instigate, it has been reported that at least you need a good high temperature, in this case at least about 150 Celsius. But in coal reservoirs, especially in Australia, you don't find reservoirs, very rarely you find where it exceeds 60 Celsius. So this also may not be severe compared to other reservoirs. Next is proppant embedment. Now proppant embedment is basically where proppant actually penetrates to the surface. Now when it penetrates, it allows the fracture to close. Now coal, naturally, relative to other rocks, it has a very soft nature. And because of this, it is very vulnerable that these proppants actually embed. Now, because of that, this can be the most profound damage mechanism that we can expect. Having said that, although they have done research on number of other reservoirs, for coal, it has not been very comprehensively reported. And when you take proppant embedment, the main proppant embedment, the influencing factors, is the implementation process of the hydraulic fracturing, which includes the type of proppants that you use, the amount of proppants that you use, the type of fracturing fluids that you use. Second is the reservoir characteristics, and the third is the change in these reservoir or the rock conditions due to the reservoir conditions. Now the first one, it is just, you can take results from other reservoirs because it depends on the implementation process, it depends on the operator. But the second and third, it depends totally on the reservoir characteristic, it depends on the rock. Now taking results from other rocks may not be justifiable because as we know, coal has a very heterogeneous structure and very diverse material structure. Because of this, it might be not justifiable or not the best thing to do. But having said that, when you say take the analytical studies done on proppant embedment, the main property of rock is elastic modulus that decides the degree of proppant embedment. And this was shown true for shale samples, where for stiff samples, the proppant embedment was less, but as the Young's modulus reduced, the proppant embedment increases. Now compared to shale, coal samples has a very small elastic modulus, as shown in this figure. It is 3.4 and the shale samples are greater than 10. Now because of this, it looks like it's inevitable that proppant embedment must happen in coal seam reservoirs. Now the another one is, we know that with the effective stress increase, the proppant embedment will increase. But what about the production time? As the time increases, will it be the same or will it become worse? Now two factors actually suggest that this might become worse. The first one is the creep deformation has been reported in number of coal studies, And the second one is the reduction in elastic modulus with time due to the interaction of fracturing fluids and pore fluid conditions. So this also needs to be investigated further. So based on these, coal seam reservoirs, as I said, it's relatively in shallow depths. But do we actually need proppants? This needs to be investigated. And if we assume that, okay, proppants are needed, proppant embedment looks like the most profound damage mechanism that we can expect. But no comprehensive experimental study has been carried out. So my research actually focuses on these two aspects. So based on that, my main aim is to see the applicability of propping agents during coal seam gas extraction. For this, I have two main aims. The first one is to find the capability of proppants to enhance the flow performance in coal seam reservoirs. This is where we actually check whether proppants are needed or not. Now to achieve this, I have two tasks. The first one is to do triaxial flow tests on prop fractures and unprop fractures to see actually whether proppants are needed or not. And the second one to validate, is to check the fracture aperture change in coal reservoirs for unprop fractures and prop fractures. Now this will be done through multi-stage micro-CT analysis, which I'll be explaining at the latter part of my presentation. Now, if we get positive results that okay, proppants are needed, second is to check the proppant embedment in relation to coal mechanical properties. Now, first we will be investigating the mechanical properties. Here, mostly we'll be investigating the surface of the coal surface because that's where the proppant embedment happens. And then we'll be conducting embedment tests for different in situ conditions, and then to compare with the mechanical test results. And micro-CT image-based analysis will be done for all samples to quantify the proppant embedment and to get a qualitative analysis as well. And along with that, a theoretical background study to understand how the proppant embedment mechanism happens in coal seam reservoirs. So this is my aim, and as I said, the first one is to see whether actually we need proppants. So for this, I have three sections that I'll be looking at. The first one is the fracture type, how much the proppant distribution, and the maturity of coal. And once if I get a good result for that, and we need proppants, we go into the mechanical properties. Here, mostly we'll be focusing on, as I said, on the surface of the coal. And then the embedment test, as discussed earlier, I will be looking at two main factors, the time and the reservoir conditions. Under time, how it changes with saturation time, and the reservoir conditions are the pore fluid condition and the stress. So my first experiment series was, again, as I said, if are proppants needed for coal seam gas extraction. this is to address one of the issues that were brought up during my 6-month review. So I used a bituminous core sample, and the propping agents was graded 2040 sand, and the injection fluid was water. So the experimental procedure, I had 2 cases done in sequence. So done 1 and then to 2. So basically both are same. The only change is the filling between the coal blocks. Here we have a monolayered proppant, the single layer proppant pack, and here we have sugar. Now the reason that I kept without keeping it empty to use sugar was to keep the initial fracture width the same in both the cases. So the initial fracture width of proppant layer and this one is same. And as the water flows through, the sugar will start to dissolve and this fracture will be allowed to close. And the confining pressure was changed from 2.5 to 15. Injection pressure was kept constant at 1 megapascal. So, but one of the issues was, number of issues came, and one of the main issues that it came was the sample preparation. In fact, it took me almost 8 experiments to get one result. One of the biggest issues was the sample preparation. Now, when you cut the sample in half, there is material losses at the edges. Now, this white places, due to the confining pressure, it will push the membrane into the sample and create holes along this fracture. This will allow all the oil inside the sample and destroy the sample as well and destroy my membrane as well. So to overcome this, I met a lot of individuals as well as the CSIROs I already mentioned. They also gave me some this one, and also after some number of strategies came to this sort of sample preparation. So we have the sample here, cut into 2, and these void spaces were filled carefully with plaster of Paris and kept for 24 hours of hardening. And then the outer surface, to remove the asperities in the outer surface, the sandpaper was used to remove it, and then to simulate the salinity condition in the reservoir, it was saturated for 1.5 months in brine 10%. So once it was saturated, this is for the case 1. Here we have the sugar particles kept here, and the wrapping paper, cling wrap was used to keep it together. And then I used a foil paper. This was after doing tests. I found that because we need to do for the second experiment, the same sample, right? So because of that, without using foil paper, it gets stuck to the membrane, and either I have to remove, damage the membrane, or destroy the sample. So this foil paper was good enough that it was able to retrieve the sample, and then adhesive tape was used to give additional stiffness, and then it was basically assembling into the triaxial pedestal. So these are the results for the flow rates of the prop fracture and the unprop fracture. Now in the unprop fracture, for 2.5 and 5 megapascal, it remained the maximum flow rate that it had. But soon as I removed or increased to 7.5 megapascal, the flow rate reduced to less than 6 milliliters per minute, which was a 93% reduction. Now this assumes that between 5 and 7.5 megapascal, the fracture had to close. Now when you take the prop fracture, regardless of the stress applied, it achieved the maximum flow rate. Now comparing these two, the proppant seems to have resist the fracture closing. Now in the next graph, we have in the left graph the maximum flow rate that it achieved. Now here, as we see in the unprop fracture, it had an exponential reduction, and in the prop fracture, it remained the maximum flow rate during the stress increment. Now in the right hand side, I have the proppant flow rate, the ratio between the flow rate of the prop fracture divided by the flow rate achieved by the unprop fracture. Now for the 7.5 megapascal, it had at least, the prop fracture flow rate was at least 1 magnitude higher than the unprop fracture, and for 10 megapascal, it was at least 2. Now this seems that as you go forward, or the stress increases and increases, the impact or the seriousness of the proppants are becoming more and more. Now after I did this experimental series, I went to the second experimental series to see how do the proppant layers actually affect. Now the main purpose was to do is to first validate the results that I got from experimental series 1. And then I checked whether the impact of proppant layers do have an effect or not. Now this, I have 3 cases. The first one is the unprop core fracture, and the second one is the multi-layered core fracture, so done in sequence, and the third one I did for monolayered proppant. Now the confining pressure was changed from 1 to 15 megapascal with 1 megapascal increments. So to see more scrutiny, to see whether it changes anything. So, and the injection pressure was kept constant at 250 kilopascal. So if I take the flow rates here, similar to the experimental series 1, the unprop fracture showed a gradual reduction with stress, whereas the prop fracture remained its flow rate regardless of the pressure applied until 14 megapascal. Now, when I go further, and this shows similar to the experimental series 1, so that the unpropped fracture showed an exponential reduction. And if you remember in the experimental series 1, it showed that the propons showed more advantage at around between 5 and 7.5. Now at 7 megapascal here, it showed at least 1 magnitude higher in the prop fracture. And as you can see in the slope here, it increases and finally reaches 2 orders of magnitude higher than the unpropped fracture. Now this shows that, again, as you go deeper and deeper, the propons are become more and more advantageous. So the next challenge was to see what effect does the multi-layered and monolayered prop fracture show. Now, as I said, until 14 megapascal, there was no difference in the maximum flow rate achieved. But after I increased for more than 14 megapascal, the monolayered prop fracture showed a gradual reduction, whereas the multi-layer did not show any reduction. Now, the monolayer to show gradual reduction, the fracture has to close. Now, for the fracture to close, because the propons are in between, either they need to crush or they need to embed further. Now, in multi-layer, why this doesn't happen is because basically you have a good concentration there, and then the number of minimum propons per area is more, and because of this, the stress applied for each propon is less, and because of that, at this stage there may be not any propon embedment or crushing. But even if you assume that propon embedment happens just like in the monolayer, the fact that it has number of layers to keep the fracture open, it may facilitate this flow performance. Now in the second one, I saw in the experimental series 1, the time taken to reach the flow rate had a gradual increase at first, and then it settled. Now if you take the second experimental series also, for the monolayer, it had a gradual increase, and then there was a steady state, or the time taken was steady. Now this was because at the initial stage there is some propon reorientation or propon distribution, and this causes more resistance, and this resistance are shown in the time taken. Now if you take the multi-layer, it doesn't show a steady state at all. This is because when you have more and more concentration, the vulnerability of these propons to move, regardless of the pressure, is more. And the other thing that noticed was the time taken in the multi-layer was always more or less higher than the monolayer. Now this is because of the tortuosity in this propon pack. When you have more and more concentration, more density, the tortuosity in this propon pack is high, and that's why it takes more time. So basically when you look at experimental series 1 and 2, it appears that above 5 and 7 megapascal, which is 650 and 800 meters, the advantage of propons is more telling. And the number of layers did not show much difference, but for greater stresses, 14 megapascal, above 1300 meters, the multi-layer showed some sort of an advantage. So far in this, I have completed the literature review. And I have done in the M1 for the fracture type, for the unpropped and non-propped, and also the propon distribution for the multi-layered and monolayer. So in the future work, as I said, for the AM1, I'll be analyzing the fracture aperture change. For this, we'll be using a specially designed cell where you can scan under stress. Now, to scan under stress, you will have for unpropped condition and propped condition, and you can see how the fracture changes under stress for different confining pressure. So this will give a fairly good idea how it changes, how it evaluates compares between the propped and unpropped. And then the embedment test. Now embedment tests here normally done in shear samples, they use this equation. But as I said in the previous report or the previous results, we saw some sort of propon redistribution happens during the initial stage. Now because of that, taking that as the reduction in fracture aperture may not be good. So for that reason, I'll be using a steel plating here, steel blocks, and compare that with the cold blocks done for this, and so that the uncertainty of propon quantifying or the propon embedment quantifying will be less. So one of the ways of doing quantifying the propon embedment is to do the micro-CT analysis. Now the propon embedment, as you can see, this is the experimental series 1 sample that I used. So you can see that there are a number of indentations caused by the propons. Now you can do a micro-CT analysis for this, and you can construct the sample. And if you can see, there are indentations shown in this sample. So I divided this into 3 volumes, and then you can segment all the indentations that are found in the sample for different depths. And this, you can plot the graphs with the depth, how much for each depth, the number of indentations that you have. And based on that, you can get an average embedment depth. In this case, it was 0.032 millimeters. So this is where I stand so far, and hoping to continue. And I have submitted 2 review papers, one in FOIL on the proper degrading mechanisms, and the second paper was in petroleum science and engineering, which I got comments, and the coal composition, and also have been fortunate enough to get access to the Australian synchrotron facility twice, and I have submitted another proposal as well for the second round, and completed the 2 post models. So I would like to thank my supervisors, Dr. Samantha, Professor Stefan, and Professor Nabil, especially Professor Stefan, for initiating the experimental series 1, and technical support given by the lab technicians, the TRACES platform, obviously, and the Australian synchrotron facility, and obviously my research colleagues from Melbourne and Monash. So thank you very much.
Questions?
So you have a question to ask for Maki? No question?
Okay, I'd just like to go ahead, and I'm very happy to see that you did actually carry through this analysis. I think it's very important to clarify things and to understand, first of all, in which sort of condition window the use of poppins might be actually beneficial. So I think you've got some conclusive results there. So my first question is, however, concerning the case where you didn't have any poppins in the fracture and the case where you did have poppins in the fracture. And here we're looking at 2 systems. I mean, the first one, where you have a channel flow, it's essentially flow between parallel plates. You get a parabolic flow profile. The second one is porous medium flow in the presence of poppins. And I would have expected to see a considerable difference in the flow rate for the open channel flow. Can you see that? I didn't see that in your data.
So if I take the case 1, right?
So somewhere you did have a comparison between
yes, so this is actually the unpropped fracture. So I have pointed out with the confining pressure the flow rate for the unpropped fracture. So initially it had a maximum flow rate, and then it reduced to less than 1 at the end for confining pressures at 14 megapascal.
Yeah, see, this puzzles me. This is not right, because in the unpropped case at the very low confining pressure, you should be much above the propped case.
Yes. So in this case, the problem was the pump was used. The maximum flow rate given was 90 milliliters per minute. So that's why I got 90 milliliters per minute, and then it reduced.
But it is super important that you show that. Yeah? No, it's not just a little thing. It's an order of magnitude at least more permeable if you don't have any poppins in there under no confining stress.
Then you can't go for very low injection pressure to reduce the flow rate because,
Yeah, you can calculate it. These are planar surfaces.
Yeah.
We know what the parallel plate flow rate is,
Yeah.
just for water. So that's the first thing. And the second thing is, so show that, and that must be in the paper very prominently, to say to people, at that above it, at a shallower depth than that, if you put poppins in, your flow rates are actually going to be reduced by 1 or 2 orders of magnitude, depending on what that fracture aperture is. Second point was that you draw a conclusion that at around 650 meters depth, or a bit at a greater depth than that, you will start to see closure of the fracture in the absence of the poppins. Also, the poppins will really support the fracture. However, I did just a back of the envelope calculation while you were talking. I think you just used essentially no pressure in the fracture as an assumption here. And if you have a hydrostatic pressure, then the density difference here between the rock and the fluid determines the effective stress acting on the fracture.
Yes.
So this is not taking effective stress into account.
This is actually, so what I did was, when I calculated the stress, I first used the 2.5 specific gravity, but then I found the research article. So this is actually taken from a published article. So here they have used, the blue line shows the average effective stress curve that they have developed based on all the coal basins using in Australia.
This is fantasy, this curve. No, this is site specific. I mean, this is not. It will never look like that. It depends really what's resting above that coal seam. I mean, it can be a loose sand with a density of 2,000 kilograms per meter cubed, or it can be a super strong rock at a density of 2,600. So it will never look like that. So just doing a simple calculation where you say, okay, your density is 2,500, which is very high for rocks near the surface, and the water density in your fracture is 1,000. That gives you a density difference of 1,500 times 1 kilometer times G is only about 1.5 megapascals.
That's the curve that I put it here. So this is, if you take just like that, this is the effective stress curve. If you take 10, and the same way that you said. This was
and
the.
that puts you deeper down. That means it's deeper down.
Yeah.
And that's also what's borne out by your observations on any sort of mining activities, caves and whatnot. If you are at a depth less than 1.5 kilometers, you almost do not need any support to keep cavities open for hundreds of thousands of years. If you're below that, they will gradually close. And the deepest mine in the world, Western Deeps, former Tautona mine, 4 kilometers depth, the walls converge at 5 centimeters per day. So this is the sort of the backdrop, given the typical mechanical properties of rocks in the shallow grass that plays into this. So I'm happy to, with your conclusion, but I think you have to revisit this particular point. If of course, they do some coal seam gas operation and they draw the pressure down to atmospheric to produce the methane gas, well, then you're right. Then at 650 meters or so, you may already be in trouble. Although we go caving on a routine basis at much greater depth than that. So it depends a bit on the strength of the rock. If they just drain the water out of the coal seam and then they produce at, well, near 1 megapascal, quite different conclusion. Then they can happily do that to 1.5 kilometers. So that's all, sorry. More comments than questions, but yeah.
Can you go to the image you had that you put to a stainless steel or to a steel?
Yeah, this one.
Next one. What's the objective here of the two comparison and what do you expect to see?
So if we remove the steel platings, if we remove the stainless steel that we are not using, and we calculate and we apply the pressure here, and we calculate based on this, normally we use this equation, total deformation, minus the Proppen deformation we can calculate, and then we can remove the sample deformation, and that will give the Proppen embedment. But if I use just only this, there is some Proppen redistribution. There will be some movement in this Proppen, and then this causes the Proppen to be, the fracture to close at least a little. So to remove that uncertainty without taking that as also the Proppen embedment, to reduce that uncertainty, I'm using this steel platings to compare with this.
So you're putting a very stiff material.
Yes, exactly.
There was one with the depths, the indentation with depths. Can you go there?
Yeah.
So I do get it, but what's the objective here again? Because one would expect that to happen anyway, wouldn't you?
Yes, I would. So at the experimental stage, I'll be getting some information on the Proppen embedment depth. So this is actually to validate the results, more quantitative as well. And also it is, we can actually look at what is the maximum depth, what is the depth variation along with the embedment depth. So that gives a better.
Are you going to take that, are you going to develop a model then to predict the flow, or you are just doing an analysis of the indentation with depths?
At this stage, yes, I'm just analyzing the embedment depth. But
he's going to come up with something theoretically, but first of all, he has to check how the embankment change with the reservoir condition and various factors. So he's studying all that one. So temperature, pore fluid condition.
But this particular one, you have that's the depth from the surface.
Yeah, there is only one.
And as you go deeper in, there is less indentation.
yes, so this is actually, so this is at the initial depth, right? So when you're going to deeper and deeper, the indentations go beyond or smaller. the amount
No,
of.
no, I'm not questioning the result. I just have difficulty putting it in place with the rest of your research. I don't know. You know, if you said that, well, I'm gonna develop a model of that channel, of that track, and then run a numerical analysis to predict the flow, and hence these things are important, then that would be, you know, an answer, possible answer. But yeah, anyway, I have difficulty putting it in place with the rest of your research. That what's the significance of doing this?
Yes, initially to validate the results that I'm getting from the experimental results, from the equations that I'm getting, what is the embedment that I will be validating from this. And secondly, I'm planning to do a theoretical study, and that this also will come into place because I'll be using some numerical basis as well to support my theoretical study. So then I might use this.
Also have a comment. There is a triaxial chamber there, the image before. It's a comment I'm making here, not a small one that you're going to use for imaging. Yeah. Because there's another PhD student in the team that is this your design or his design?
Their design, so from DCI SIT.
So you are just using the device to get results.
Actually,
Yeah,
we gave the diagram, so it was designed by.
Yeah, but one of these guys, my point is that one of these guys can claim it as their work. You cannot just both come and say,
So
I've
they
done
have-
this
they
and I've done
have-
imaging,
yeah.
and it's
They
okay
have-
to help each other.
Mhm.
But if your experimental work or his experimental work, there is a section of it, design of equipment, then one of you can claim. It's okay, it's either of you. I don't think it's right for both of you that take credit. And I think that's a matter between the team to resolve.
Could you go back to the previous slide? The one that showed the experiment, yeah, that one. You have the, what sort of scale, spatial scale, the fracture and the proponent? I couldn't figure out. Are they the same size, like that?
So this is just a schematic diagram that I've drawn. So the core samples are of 38 millimeter by 76 millimeter size, and the prop.
In reality, what would be the size in real life? You know, when
In
you do
real
the
life,
fracture.
The fracture is quite small than this, what we expect here. So the fracture here, if I measure through vernier caliper, it's around 1 millimeter.
Okay.
But
What is your proponent propant
size?
size?
So propant size, I did another analysis for that. So it is around 400 micrometer to 800 micrometer for the 2040 graded sample.
Okay, for this case, the previous diagram doesn't make sense to me. That's fine. I understand now. It's small.
Yes, it's very
But I mean, the fractures have a power law, length, frequency distribution.
Mhm.
Yeah. So there's no characteristic size.
Hmm. Well, I think we are running out of time because we move on to the other room.
Yeah.
Okay?
Yeah.
Or these guys can really
Yeah,
continue.
thank you for coming, and you can.
Whichever way you want. How about your service?
So we can go to the.
We will now.
Okay.
Thank you.